Hi, my name's Andy, and today we're going to do a little bit of arbitrary precision arithmetic. So we're going to try and make a number that can be an integer number that can be as big as you want it to be, just based on how much memory you've got on your computer. Now, there are crates for this. You definitely don't want to do this yourself, but I thought it might be quite interesting to see how it goes. We won't be doing anything too difficult this time. I'm probably only going to do adding up and subtracting. If we're lucky, because I don't feel up to the difficult bits. I don't know, maybe multiplying would be okay. Anyway, so maybe just a nice short video, bit of arbitrary precision arithmetic just for fun. Before we do though, quick shout out to Andy Smith, who went through my previous video about fizzbuzz, where I was like doing it right, doing the best possible fizzbuzz I could, and did performance testing, like benchmarking on the different versions of my the code that we did together, and discovered that the version that I was really happy with at the end, which I thought was really performant, was the worst performing of all the code. So thank you, Andy. That is it's a perfect demonstration of how you should never optimize your code without measuring it. And so maybe at some point I'll do a video where we do some measuring of performance and try and make it better. In fact, I have been watching some billion row challenge stuff, which looks really cool. And I might possibly at some point do like a very not as clever as all the other people version of that. And then maybe we could talk about how to measure performance a bit. But anyway, thank you, Andy. Great demonstration. Don't listen to me, and don't try and improve performance without measuring, because you'll make it worse. And you make your code worse, everything will be worse. Okay, so on to arbitrary precision arithmetic. So what do I mean? What I mean is we're going to make some kind of struct, which we'll call, well, let's call it arbitrary. So there must be a better thing than that. So anyway, okay, so we're going to make a number be some kind of arbitrary integer. And I don't know, maybe you can make it from a string, because it could be like really, really long list of numbers. But let's imagine in this case, it's a 2. And now let's have another one. And maybe that could be 3. And then we're going to add them together. Can't type today. And then we're going to print out the answer, which would be like 2 plus 3 equals Z. And presumably these things are going to be able to print themselves out as well. So we need to make this arbitrary thing. And in a minute I'll talk a bit more, because I don't think it's going to look exactly like that. But anyway, yeah, so let's have some tests. I seem to just not be able to see my keys today. I don't know why. All right, so let's make a test, which is, let's just say small numbers can be added, right? And we'll do a test that's something like that example. Small numbers can be added. Is that the first test we want, or is it just that we can create? I think the point about creating them is you won't actually know you won't know whether they work or not, right? So we could do something like serializing to strings or something, but we'll do that later. So in fact, for now, let's do a debug print of this, and then we save ourselves from this, at least turning it into a string for a while. All right, so let's just do this. And then make an assertion. And I guess the assertion we want to make is that Z is equal to the result of parsing that, and I kind of feel like for completeness we should also say that z is not equal to the result of parsing that, right? So like, because otherwise they could all just be, there could be some trivial way of making this test pass, and we want to make it. All right, so now we can add things up. Let's just say sanity. Not all arbints are equal. I don't know why I felt I needed to do that corner case, but anyway. I guess I want my test to push me to do something useful. So in order to get this to compile, we're going to need an arbint struct. And it's going to need a from method. So do we want from or do we want from? I think maybe we want to call it from str, right? And we'll just not make it a conversion. Do we want that? I don't know. Well, let's try making it a conversion. Maybe it'll work out nicely. Let's see. Impl from ampersand str for arbint. Just want to make it compile first before we do anything else. So we won't implement that yet, we'll just make it compile. And then if we want to be able to add them up, what we're going to do is that. We need to bring in add from studops. And that's also going to have, oops, an implementation, and the output of adding two arbitrary ints is an arbitrary int. And it should be debug. Assume we're going to have a failing test. All right. Well, no, we haven't quite got a failing test yet because we need to bring in some stuff like so. And we need to be able to compare them. And later we'll think about whether the automatic implementation of partial eq is good enough for us. Hopefully it will be. Okay, so now we have failing tests. Yes, we fail at some of our to-dos. So let's implement some of these to-dos. So first of all, let's do a trivial implementation of arbint. Let's make it be actually a U8. And that's it. So now we can do that. Well, no, not that. This. I think. Kind of implies that we should have a parse for. Okay, and that sometimes goes wrong. Okay, so first thing is this should be. I think we should have a parse, just like we should have a way for parse to return an arbint. How does that work? Parse can parse into any type that implements the from str trait. So let's make the from str trait instead of this, and that will, I guess, return a result. Bring in from str. Right, yeah, and it might have some kind of error, like, well, let's see. All right, so now we're going to do s.parse. So our value is going to be the result of parsing the str we were given into a U8, and if we question mark it, then we're going to return an error of some kind of type. And what type of error does it return when we're parsing a U8? I wish it told me. Let's make it be something it's definitely not, and then hopefully our error will help us. Oh well, we need an OK wrapping this. Now we get the error I was hoping for, which is parse int error is the type. We may need to change that. We'll see. But that's a built-in error type that's used for parsing ints, and we are parsing an int, so maybe we can use it. It would be nice if we could, wouldn't it? All right, so we need to just unwrap here to make this work, and also I guess down the bottom. So now we're returning a result from. Oh, hold on. From is not even. Oh, okay. It shouldn't. It should be from str. I didn't realize there was when I proposed from str. I didn't realize there was a trait called from str. Or yeah, maybe that would have been the right thing to do. Anyway, the change we've made is to go from which takes which returns, like it always succeeds, to from str, which returns a result. We could have used try from, but given that there's a from str, that's exactly what we're doing, and parse uses it. So now we'll be able to say, yeah, now instead of this, we can say this. Like so. And maybe not even declare the type. No, it looks like we have to declare the type. Is this better? Maybe that's better. We want to be able to do both. So let's just put one of those in one of our tests as well. Like this. Just to make sure that our tests are covering the way we want our code to be used. Alright, so when we run the tests, what happens? We still panic at line 28 because adding them is still not working. So, trivial implementation of adding is it's going to return an arbint whose value is the result of adding up. Oh, these should be dot values, sorry. The result of adding up to arbitrary ints is to add up their values and make an arbitrary int out of the answer. And look, our tests pass. Okay, so we have some kind of structure for how I think this is going to look. Was this a good time for me to complicate things? I think it probably is. So, oh no, not quite. Yeah, we'll do that later. All right, so in fact, maybe we won't do it at all today. All right, so let's get a failing test. So let's say large numbers can be added. Or let's say, I mean, they're really medium numbers. Medium numbers. And in particular, you can add, let's just not worry about this. And so that already passed, by the way. So that shows we're not doing a completely trivial implementation. Let's make our whole thing happen inline. Let's do 255.parse.unwrap plus 1.parse.unwrap should equal 256. This is getting a bit awkward, isn't it? I think that parse.unwrap needs to be in a function. In fact, it's even worse than that. Yeah, all right. Let's make ourselves a little helper function. Let's call it P for parse. Maybe that's right. And what that does is parses a str and gives us back an arbint. And it does it with s.parse.unwrap. like so. It's not going to give great error messages if it goes wrong, but it's going to make our code much easier to read, and it shouldn't go wrong, right? Like we're every time we do this, we're including like a string literal that we know should parse correctly. So yeah, it'll go wrong occasionally, and it should be easy enough to find. Okay, so that's a bit easier to understand. Should we replace this test with stuff that's that easy to understand, or is this okay? I think that's okay. We want to be able to make it explicit that these things are supported. All right, so I think this test is going to fail because currently our arbitrary sized integer is not arbitrary sized, it's just a U8. It fails because we attempted to add with overflow. All right, so what is our implementation of an arbitrary int going to look like? Well, I think eventually it's going to look like a sign and a vec of U8. And now what I was umming and ahhing about earlier was what I would like to do is be able to write tests in these with these nice small numbers like 255, 256. But I also want, when this is like high performance production of code, I would quite like to be able to do arithmetic with U64s if I'm on a 64-bit system, because I think that'll be a lot faster than fiddling around with a load of U8s that are all probably packed into one U64 or not, or, you know, wasting space or whatever. So I would quite like arbint to be like an arbint of t and have a vec of t in it, and then t is some kind of thing that is unsigned integer like. But what I'm going to do is put that off, either for later in the video, but probably for like another video if we feel like it. Because for now, this vec of U8 is going to do its job perfectly well. Okay, so now, what should we do? Well, first of all, we can do like quite a trivial implementation of this, which is, this will work sometimes. Whoops, that's not going to work. This will work sometimes, and actually it will work in all the tests that we currently have. So just let it be a vec of exactly size 1. Oh no, it's not going to work in every case we have. All right, we have to do better. Oh, fine. Okay, so all right, let's do better. So how are we going to do this? So I think what I'm going to do is I'm going to have a vec of U8s where the least significant byte is first. So basically, the basic plan is going to be, instead of our numbers being an exact number of bits, we're going to have as many bits as we need to represent them. And the first 8 bits are going to be the first value in the U8, that like the smallest 8 bits are going to be in the first U8, and then if we need more, there's going to be another U8 to represent the next 8 bits, and so on. So how am I going to write that in a way that's understandable? It's like a little endian. It's like a big endian. What endian in this is it? The weird one. That's little endian, I think. Yeah. It's like a little endian. I think it's a little endian representation of the number. Least significant byte is first. I think I've written that right. I mean, I know that least significant byte is first. I'll put that in brackets. Apologies if I said it the wrong way around. Okay, so how are we going to do parsing numbers? So I think what we're going to do is, are we immediately going to jump to something clever? I think we are. So we did like parsing numbers in another video, so we can quickly jump to the solution of it, but we need a good test for this. So let's start off with, and we're going to have to do converting them back into strings to make this testable. So we're going to do can parse medium numbers. We're basically going to have to stop leaning on the existing parsing, I think, because we're parsing the base 10 number into effectively a base 256 number, and they won't match up. So I think we're going to have to do it manually. So let's say equal. Well, let's use arbint. What do we like? I think we like arbint from str. No, we've got a p. So let's parse 256. No, let's do 257 since we've done 256 below. And then we're just going to turn it into a string. Oh, goodness, typing. It's going to get turned back into a string. Like so. When we do x.toString, is it? Why not? Why not? Oh, come on, typing. Right, so that's going to fail because currently we don't implement std format display. So let's implement std format display. Excuse me. So when you're writing your own number type, you have to make a lot of you have to implement a lot of traits. Like you have to do all the different adds that you want to allow and all kinds of things like that. Oh, that should be for arbitrary. No, I think there's two different displays, and that's why I've left that more fully qualified than the other things. I can't remember. Don't care. Okay, so to display a number like this, we are... How are we going to do that? We can have a number of bytes, and we probably want to start with the biggest one. You know what? We're going to put that off for a little bit. We're going to put that off because that needs thinking about. Okay, so instead of that, we're going to do a real horrible cheat. Just so we can think about things one at a time. So what we're going to do is we're going to make a U1 to 8. And then we're going to add to it for byte in value, self.value in plus equals b times. I mean, we could go backwards through them. Okay, right. Let's just let's have a multiplier. This is just the worst thing I've ever done. I'm so sorry. We multiply b by multiplier, and then we multiply multiplier by 256. And we can turn a U8 into U1 to 8 like so, right? I think it just doesn't know whether to turn it into a U1 to 8 or a reference to a U1 to 8. Oh, for goodness sake. So I think what we just need is to be more explicit. So there we'll have a U1 to 8. And convert our U8 into it. Oh, I'll tell you what, we need to convert the B before. So this multiplication will fail because it's multiplying U8s. So actually what we need to do is let mut A equal B dot into, and A is going to be a U1 to 8. And then we're going to multiply it by the multiplier. I mean, this is just the absolute worst thing to do. And it's getting more and more complicated all the time. Yeah, we're getting there, Okay, so this should be going through. Should be star B. Maybe in brackets. Okay, all right. So now we've got an N. We can print it out. Right. What do we want? Right. Format. N. Like that. Can we do that? What is it? Right. Oh, we probably maybe just want right, the macro. Yeah, we want the macro. That's what I was that's what I was reaching for. We need to write into something, which is F. Okay, so a little apology. Well, not actually doing arbitrary precision for string formatting. Anyway, so what else? So you can't add a vec of U8 to a vec of U8. We've got to do better. So adding is where we're going to do the real work for arbitrary precision arithmetic. So let us not do that yet, because we need to get our parsing working first. So let's replace this with a to-do. We know some tests are going to fail because we've got a to-do in here. That's okay. We won't look at them. So parsing medium numbers is the test that we care about, and that is failing because our parsing code is still just using U8 parse. It's doing this, and that's no good. So instead of that, we need to do something which is... I guess we can have a mutable string. No, we need a mutable vec of... Hang on, how's this going to work? Parsing a string. Yeah, we need to do... I guess we might need to support multiplication of arbitrary ints in order to be able to do this. Because let's write the implementation and see where we get to. If so, we'll probably need a way of creating arbitrary precision integers that are not like from a vec or something like that. That's just less difficult than parsing them from a string. Gosh, I thought this was going to be so simple. We'll just do adding up. We won't do anything else. Anyway, so the algorithm is going to look something like for char in s dot chars. Let x equal char dot parse. If char has a parse, does char have a parse? Two-digit. Yeah, in the base 10. So now x is the option of U32. So we'll do an unwrap here for now, which is obviously wrong. And now we've got that digit, we can add it to our total. So we're going to have an arbitrary int here, which is mutable. which we have to somehow create, so we're going to have to do some kind of new from a vec, which just contains a 0, some kind of way of making an arbitrary int without calling this function we're writing. That seems as good as any. And then total is going to be add x, and then if we're not at the end, we're going to multiply total by 10. So how are we going to know we're not at the end? I mean, we could just divide total by 10 at the end, but that would be a bit dodgy. We could enumerate this, so then it would be I, comma, ch. Is there a better way than doing this? I don't know. Let L equal S dot. Oh no. We need to know how many characters there are like that. That seems really awful. And then if I is less than I minus 1, maybe, although we'll have to test to check this is even right. Now we've got a total, then that 10 total is the answer. Like so. Okay, so we've got to implement our new method for arbitrary, which is just a way of directly constructing an arbitrary int, like so. This will be value. Just make one, and it's going to be a vec of u8. And how's it going? So we need a plus equals and a times equals for this to work. So this is all just a big to-do, really. So let's not have it yet, because I want to do the maths before we do the from struct. I've changed my mind. So we'll ignore this test, and we'll allow making these arbitrary ints like so. And I guess now I kind of want to call this n2 and this n3, just so that we know what they are. Or what they're supposed to be, maybe. And then this should be a 5, I guess, so we'll call it n5. n2 plus n3 equals n5, that sounds right, doesn't it? Or maybe this should be just called answer. Because we don't know it's a 5 yet. And then we'll just say, same as before, it's not equal to 6. Okay, so let's also do the same thing here. Yeah, let's do the same thing here. Which means we don't need our p function for now. Unless we use it there, but that's just... I don't think we need it anymore. For now, maybe we'll need it later. We've got to declare its type, that means. And then here, this is going to be an arb_int. New with a vec with a 255 in it. We're going to want tests that do the other thing, because this is going to end up being quite hard to read. Like, because it's assuming all the internals. When you add a vec of 255 with a vec with one thing in with 255 to a vec with another thing in with 255, then you get a vec of 1, 0. No, 0, 1. Right? The least significant. So it basically, this is going to be 256, and 256 is represented by a 1 with 8 zeros. So the 8 zeros are this least significant byte, and then the 1 is here, I think. So how are we getting on? We've got a panic on line 65 for both of them, because adding is not done. Fine. So we've got to make adding work. Let's start off by making the easy adding work. Is this too easy? Am I just avoiding that problem? I don't know. So what's the easy version of this? It's just, I mean, the really dumb way is to say it should be a vector with one thing in it that adds up the first thing in each of the other things. Okay, that passes. So I hate it and it's dumb, but it made our test pass. So now let's unignore a harder test. Watch our test fail. And there is overflow. So what we need to do is, when we're adding up two arbitrary precision integers, we need to loop through both of their vecs. And I think this is why I wanted it to start. I wanted it to be kind of little endian, because I want to be able to loop through them in tandem, starting at the smallest thing, and then being able to carry over later, and they'll be in lockstep if it's little endian. Otherwise, we'd have to like walk backwards through them, and it would be harder. So I think this is the right thing to do. Anyway, so there's going to be some kind of answer, which is going to be a vec. And then we're going to loop through all the bytes of both self and right hand side, but we don't want to zip. You see, I would say self.value dot iter dot zip, but I want to zip and get zeros if they're missing from one side. Well, hold on, I'm being too clever already. Yeah, all right. So I'm trying to implement the full solution instead of something that will just pass our like, it's a reasonable way of passing our first set of tests. So let's just make 2 iterators for now. Right hand side iter. So now we've got a way of looping through both of them. And why is it complaining? Oh, I need to know what type it is. U8s. I mean, that'll maybe actually mean if we just put it as the answer there, maybe we don't need to annotate it now. Because it knows. Yeah, it's just complaining. It doesn't need to be mutable. Fine. So what we're going to do is loop through both of these iterators. We're going to stop if they're both none. But if either one of them is not none, we're going to carry on. So let's get a hold of both of them. self and right hand side is how I'm calling these. These need to be mutable. Malleable. Like so. Now we've got an S and an R. So if S and R are both none, then break. Otherwise, we've still got at least one. So we need to make the one, any that is actually none, into a 0. I think that would be. I think that'll work. 8. This is a reference to a U8. Well, I don't want it to be a reference to a U8. I want it to be a U8. Can I do that? Or that maybe? I don't feel like... Okay. Is it going to let me do that? I hate it. I hate it. Okay. I'm hating a lot of things today. Alright, so... Similarly. So if S is none, then it should be 0. If R is none, it should be 0. I think this is... I just... Can we do into iter on these, and then we'll get U8s instead of references to U8s? I think we can, because self and right hand side are both being passed in by value. So now, I think that's going to make this look nicer, and also just, it's going to feel nicer to me as well. Yeah, okay. So now we've got an S and an R, which is either whatever was in the vec, or a 0 if we've got to the end of that particular vec. So now we're going to add them up. The two U8s, we're going to add them up. So it's going to be S dot. Now what we want to do is some kind of add. We don't want it to panic. We want it to be checked. Returns none if overflow occurred. No. I want carrying add. That's what I want. Calculate self plus right hand side plus carry. No. That's what we'll use in a minute. I want... a way of telling me that you've overflowed. I want checked. It must be checked add, right? Is that right? Checked add off. Returns an option of self. I want it to be not just checked, but giving me the answer. I'm sure such a thing exists. Wrapping add is not what we want. And we could do a saturating one, but that would just, yeah. I feel like there must be. Assuming overflow does not occur, that's no good. Strict add. We definitely don't want to panic, so that's no good. Unbounded. Saturating add. And we could do that. We could do a wrapping add and then do a saturating add if it overflowed, but that just feels like, why are we doing two operations here when it should be just one? I mean, I'm close to just doing this and then fixing it later. This is it. This is it. Overflowing add. That's what we wanted. Okay. So overflowing add is going to return a bool to tell us whether we overflowed or not. So it's going to be like answer, comma, overflowed. Add them together, tell us whether you overflowed. So either way, the answer is going to go into... Is there like an overflowing carrying add? No. All right. So, okay. Let's think about this for a second. All right. So we've got the answer is definitely going to get added to. Oh, we can't call that answer. Let's just call it. What did I call it before? Result. I don't know. Answer gets result put into it for sure. And if we overflowed, we've got an extra little bit that we need to add in as well. So the next time around the loop, we're going to have more than just R to add. We're going to add S and R and potentially this one more thing. So I guess that means that we're going to need some kind of overflow. That goes around to the next time around the loop. But what if they're both already 255? Then we're going to need to overflow more. Let me think about this. Then what can we do to make our test pass before we go mad? Well, what we could do is we could say, just for now, we could say prev overflowed is false, and then we can say if you overflowed, just set prev overflowed to well, either way, set prev overflowed to overflowed, and if prev overflowed, we're going to add one more to result before we do it, and we're gonna do saturating add or something like that, right? We'll do something that is wrong, and fix it later. So we can think about things one thing at a time. The result needs to become saturating. Result of doing this addition, but I'm wondering now whether we can do some kind of saturating. No, fine. We'll do result equals result dot saturating add, which means that the result needs to be mutable. And let's see whether that works. It's failed our test that we already had because this overflow thing means that even if they're both none and pre-overflow and not pre-overflow, we need to come around the loop one more time if there's still an overflow. Hey, look, our test passed. Okay, so let's think through our code. It feels like a total mess, doesn't it? So, by the way, at the moment, our numbers are still unsigned. But yeah, so when we're adding up two of these numbers, we make a new vector, which is going to store the new number. We iterate through both of them, starting with the least significant digit. And we have this thing for like, I guess this is like carry, isn't it? Carry. And we start off not carrying. There's no extra 1 to pass on. Then we get the next like insignificant thing, and if we're not carrying anything and we've reached the end of both vectors, then stop. Otherwise, get hold of the number, or if there wasn't a number, make it a 0. And then add those two numbers together and notice whether they overflowed. And if we were already had an overflow from last time, add 1 onto our result, but we're not dealing with overflow here. And then remember that we overflowed this time, so carry that 1 bit onto the next time around the loop, and then push the answer into the vector. All right, so that seems a reasonable way of adding up numbers. Now, and I think we need to find a test case that fails when there's like a double overflow needed. I think that's the right way to think about this. So basically, where this is going to fail is when adding that extra 1 causes us to overflow, and previously we didn't overflow. Oh, so it's not actually. So there's another case which is like, what if we had? No, that's not. Yeah. So yeah, I was thinking about it wrong. The way we need to think about this is, if there would be no carry bit, except we were already carrying a bit. So what we can, what we need to think about there is that this addition here caused us to be carrying already. But if we've then got more adding to do after this, so how are we going to think about this? So our first bit of stuff caused us to carry because it was 255 plus 1. And then our next bit of stuff doesn't cause us to carry, so let's call it like 254 plus 1. But it should now cause an additional carry. So this should be something like carrying can cascade, is what I'm trying to say. So this should come out as, well, this is, what number is this? This number's easy. This is 1 plus 256. So this is 257. And we're adding to that 255 plus 254 times 256. Right? Let's write this down. So, we're adding up 255 plus 254 times 256, which equals, let's ask Python, 255 plus 254 times 256. Well, of course, as soon as I've done all this working out, we'll figure out that actually this is not the test case we needed anyway. And then we're adding on to that 1 plus 256, which is 257. So the answer, how are we going to write this? A plus B equals that number plus 257, which is 25536. So, all right. So that is what I was expecting. Like, basically, we've set up a case where the carry bit needs to carry all the way over because we get to this number, which is, I believe, this. It's 256 times 256. Let's just check that. Yeah. Okay. So that's right. So this is the smallest number that can't be represented by 2 bytes, and here's the third one because it's 256 times 256. This is base 256 numbers, right? So the left-hand digit is actual units. This is the number of 256s, and this is the number of 65536s. Okay, so I think this test is going to fail because the carrying did not cascade. Yeah, we're one less. Well, not one less than the right answer. Yeah, we're just wrong. So, how do we get the carrying to cascade? I think it should be. We should do overflowing add here. And okay, the point is, if overflowed was already true, then it can't be the case that this will also overflow. I think that is the situation. But that would be explaining why. So overflowed should be mutable. This code is so awful. Let's make it better in a second. Oh no, let's call this overflowed. Oh goodness, let's call this overflowed 2. So we need to. This is just such a mess. I'm so sorry. You must be hating me. All right, so result is going to be res2 and overflowed I guess I want to assert that only one of overflowed and overflowed 2 is true. Something like this. Can't overflow. Can't double overflow. And then overflowed should be overflowed 2. No, it should be overflowed or it should be overflow should be true if either this overflow happened or that overflow happened. What are we complaining about now? It needs to be mutable. Oh, that's what it's complaining about. Okay. Never mind. Okay, so first let's check whether we've made our test pass. Oh wow, look, we've made our test pass. Oh gosh, it's just showing me that this should be... I think a question mark here will be the right... Yeah, okay. Okay, so let's go through this code and see if we can make it nicer. And I think we might be near the end of the video. I thought we were going to do subtraction and negative numbers and things like that, but this has been way more complicated, as ever. It's been way more complicated than I expected. We haven't done formatting of these numbers. We haven't done parsing these numbers because we need multiplication for that. All we've done is adding up arbitrary precision numbers. Maybe we'll continue with this another time, or maybe I'll decide that this was just a total disaster area. Anyway, I hope you enjoyed it in the meantime. So what we're doing is we're looping through 2 iterators, and zip won't do it for us because we don't want to stop when the first one's finished. We want to stop when the last one's finished. So we could do we could extend one of the iterators with zeros to make this just feel a bit nicer, and then we could zip them using just the length of the vectors. It feels like that could be nicer, but this is not so bad. let's just say loop through both vecs, only stopping when both are done. And then here we can just say fill in zeros, fill in zeros if the vec has ended, or if a vec has ended. And here we just want to say when both are done and there is no one to carry. Something like that. Now we add up these two things. So S and R are the current least significant digits remaining to be added. Add them, and if the addition overflows, remember that we need to add another one next time around the loop. Fine. If we needed to add another one, to add a carried one from last time around the loop, add it to the result, and if that overflows, remember we need to carry. This is no longer wrong. So then, I just want to explain in here, if we overflowed what actual answer do you get back from an overflowing add? If we overflowed, the point is, if we overflowed when we added S to R, then result is 0. No, result is guaranteed to be smaller than the maximum U8, because we can't, if we add up two 255s to each other, okay, we got to try that. We got to try that. Before I write this comment, we need a test of adding 255 to 255. So what is that? This is just, maybe it's just another case in here. Got to be careful with that, but it's in this case it's probably okay. So if you add 255 to 255, you should get this is worth 256. So I think we're going to get 256 plus 254. Yeah, in which case I think I'm right. That's still passed. Let's just break it to check we're running that test. Yeah. All right, so these will really benefit from being parsed from strings instead of being like this. Although it's helpful to kind of see sometimes what's going on here. But anyway, if you add 255 to 255, we can do it. Then you get 510, and if you take away 510, take away 256 from 510, you get 254. And so this one here is worth 256, and so the remaining amount we need to make up to 510 is 254. And so that is what I was desperately trying to get at here, is that if you've overflowed last time, if we overflowed when we added S to R, then result must be less than U8 max, or whatever that is. Well, less than 255, let's say. So adding 1 will not overflow. The only time adding the 1 could overflow would be if the first addition of S to R did not overflow, but ended up as exactly 255. And now we want to carry 1 if either of the two additions overflowed. Alright, so that still should pass. And I can already see one way to make this a bit better, which is we could say carry equals overflowed or overflowed 2. And we don't need this. And that comment can go with that. And I can well, let's just let overflowed 2 equal this assertion can actually go here. And maybe we could get result 2 out here. Maybe this just is this. And now we need an else on this, because if carry is not the case, then it's just going to be result comma overflowed, like so. Like so. But now this assertion doesn't make sense because overflowed 2 is going to be equal to overflowed. So instead of that, we need to say if carry, then I guess we need an assertion in here. Like so. And that makes sense. Like, whoops. That makes sense that we now need to assert this when we've actually got an overflowed 2. Oh, for goodness sake. We haven't got this overflowed 2 anymore. Why is this so awkward? Let's put it back how it was. And then we're going to change our minds. We're going to say we're gonna get hold of overflow 2 out of here. And we definitely didn't overflow if we didn't even do an add. And we get two things out of this overflowing add. Then we update result. And we return overflow 2. Now overflow doesn't need to be mutable. Overflow 2 is coming out here. Our test passing. Yeah, okay. So we've slightly tidied it up. I still hate this code, but yeah. So this stuff is just to do with iteration, and this should probably be wrapped in some kind of clever iterator that we won't do. Then we add on the current digits that we're on, or current, these are bytes, aren't they? We add the 2 bytes that we're adding up, remembering whether we overflowed, because we're going to carry a 1 if we did. Then we've got to deal with the fact that we might already be carrying. If we're already carrying, we add another 1, and we remember whether that overflowed. And the answer is now the result of adding that extra 1. And then we make an assertion that we didn't overflow in both cases, because then we'd somehow have to add 2, but that will never happen, so it's okay. And then we carry around to the next time around the loop if either we overflowed on the first time or the second time. And it passes. We are able to add up numbers, so I guess now we could do some kind of very big number addition and check that it works all right. So what's a big number? I guess something too big to fit in a U128 would be nice, wouldn't it? So it'd be even better if we could print these numbers out after we've done it. But we can't do that yet. So let's just imagine that we're adding up something that we can get our heads around. So a U128 has how many bytes in it? 16 bytes. So let's go bigger than that, just to demonstrate. So we've got, let's have 17 bytes. We're going to add to that something which is just 1, 1. So that's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And the answer to that should be, if I've done it right, so there's no overflow happening here. So obviously it's uninteresting in some ways, but it kind of demonstrates that the whole thing is working. 16, 17, 18. I think that should be the answer. And if it just passes straight away, we'll be a bit suspicious, won't we? So let's just double check. Yeah, alright, so that worked the way I was expecting it to. So now let's introduce a little bit of overflowing somewhere in there. So let's have one of these be 255, maybe the 13. So that should fail. Yeah, because, yeah, it came out, it carried. So the 13, the 14 became a 0. Is this right? Oops. $14 became a 0, and then there were 2. So why would that be? You had, so that you had 255 of whatever the number of 256s we're multiplying together here is. We add 1. So yeah, alright, so this would have been the 14 because it was 13 plus 1. Instead it's a 0, and 1 got carried over to here, and then we continue as normal. So let's just make a double carry happen. Let's make a triple carry happen. This one will also be a 0. And this one will be 17. Is that right? I feel a bit worried that we need double carrying to happen. Oh, no. Yeah, it's because I've done that wrong. Yeah. Okay, so are we right? So we had 255, we added 1. And then we had 255 and added 1, so that would be 0, except we carried 1 across. And then the next one. So that seems fine. We were going to do a triple though, weren't we? So I predict that will be 0, 1, 1, 18, 18. Yeah, it looks like it is. Cool. Alright, so we can see that carrying is working. We can see that carrying is working to cause like an additional, like the vector get 1 longer. This would be just so much more convincing if we could turn these things into strings and if we could parse them from strings. But parsing from strings is going to require multiplication, which is going to be considerably harder than addition. I mean, not impossible. And turning them into strings, that's going to take a bit of thinking about. I'm not actually sure how to do it. So I'm definitely not going to try and figure that out in front of you. Instead, I'm going to say, I hope you enjoyed thinking a little bit about what arbitrary precision arithmetic would look like. Obviously more complicated than I was expecting. But yeah, the idea that it's going to be a vec of U8s, which in some sense represents the same as like a U32 or whatever is like an array of U8s in some sense, right? Like it's just a bunch of bytes next to each other and the bytes are kind of more significant. It's like a kind of, if you think of it in terms of bytes, it's like a base 256 system. And this is essentially the same kind of idea, except it's an arbitrary length, base 256 number. And as I said, I actually think if you wanted good performance, I think you probably want these to be U64s if you're on a 64-bit computer, because then the operations are going to be making the best use of your CPU, I think. So I would probably want this to be generic so that I can still write my tests using nice small numbers, but also have it be performant on different size systems. Hope you enjoyed. Let me know if you would like me to do more things like this and more teaching type things. I've got a few things like maybe around async and things that I might want to talk about teaching wise. There was something else I thought of the other day as well. Oh, trait objects and stuff like that maybe. So if you're interested in that kind of thing, let me know. If you enjoy like watching me wander my way through and get totally lost in stuff like this, let me know. If there's a little coding thing that you've always wondered, how do you code that up? Let me know. Maybe I could give it a go. See you next time.